So in the context of this Earth system construct framework models, generally they are referred to as ESM, Earth system models. At some point it started to become obvious that it's not just weather and climate. There are lots of feedbacks, and human beings are an integral part of this Earth system. So the Earth system models began to evolve out of the atmosphere ocean general circulation models, with separate evolution of land models, biogeochemistry models, land ice models, sea ice models, which started to be coupled, as we briefly saw in the last chapter in terms of the evolution of models from the 1950s onwards, the components of the Earth system. The trends that have caught our attention and made us realize Earth as a system has to be understood and modeled for reliable projections for where we are headed. So population has grown super exponentially over the last few decades, and projections vary, but they are expected to continue at least, let's say, 9 billion, unless the education of women and that impact on fertility rates and so on begin to turn this around much before 2050. Water use in terms of thousands of kilometer cubed. The transportation, million motor vehicles, which obviously contribute tremendously to greenhouse gas concentrations. Real gross domestic product has continued to go up despite the population. So the disparities, climate justice issues, significant contributors to climate change, and people who actually bear the brunt of climate change and so on are all hidden within that. But this definitely comes with a tremendous increase in energy use in exajoules here. All are going from the Industrial Revolution to 2010. Okay. Obviously, all the economic growth has come from energy use, and the energy production has relied heavily on carbon intensive sources. So the battle is well defined there in terms of reducing the energy intensity of GDPs and carbon intensity of energies. Okay, that's kind of foundation for many of the policies and agreements. Telecommunications, clearly billions of phone subscriptions, and in the Earth system trends we have corresponding to those atmospheric CO2 concentration, surface temperature with its natural variabilities, but more recently now, decade to decade, temperature change at the global scale is very strongly related to CO2, whereas here you can see that there were still ups and downs. The data has not been extended here, but ocean acidification in terms of the increased hydrogen ion here, not pH, tropical forest loss percentages, another contribution to land use change and CO2 emissions. Marine fish capture, many have become already unsustainable. Nitrogen in coastal zones because of agriculture and fertilizer use, right? So what are the main attributes that the Earth system models ideally should possess? This is from the chapter, so I'll just list them. It should include an ESM, Earth system model should include representations of all the processes and their interactions that are believed to affect climate, both natural and those perturbed by human activities. So humans become immediately an integral part of the ISM that is worth its salt. Such processes would be generally well depicted with parameterizations known and modeled accurately. This is kind of a thing that has to be looked at carefully. What do we mean by accurately? Where do the uncertainties actually come from? ESM should reflect a recognition that some aspects of the climate systems are inherently chaotic. So at weather time scale, for example, if you have slight errors in the initial conditions of all the temperatures, humidities, etc., and you integrate forward, in a few days the weather becomes chaotic, as Ed Lorenz famously pointed out in the 1960s and led to a revolution in chaos studies. We can still predict climate for seasons like El Nino, for example, monsoon, because ocean is a slow-moving heat capacity, high heat capacity, heat content reservoir that can control the evolution of the coupled climate. Land has low heat content, atmosphere has very low heat content, but ocean can track the evolution. So even that becomes chaotic at some point, especially when you include the feedbacks, the nonlinear feedbacks between ice, albedo, soil moisture, roughness, length, evapotranspiration, everything we talked about in the previous chapter. Hence, although average changes in weather may be expected to be amenable to predictions, conditions at particular dates and places would ideally be described by probability distribution functions. So as you go beyond even a season, you begin to have probabilistic depiction of normal years, for example, normal year, El Nino year, La Nina year. So if El Nino year probability is very high, then you expect high probability of El Nino, and so on. To achieve probabilistic outputs, the model must be capable of operation in an ensemble capacity, where multiple simulations are made using slightly different initial conditions or parameter values that are all plausible given the past and current set of observations or measurements. How do we think about that in the real world? Basically, Mother Earth is starting with some initial condition and she's making one realization of weather and climate. Models don't have the exact information that Mother Nature is using, and even Mother Nature with a slight perturbation to the initial condition would go in a very different direction. So the model ensembles basically try to capture the range of trajectories that Mother Earth would have followed. And you expect that the model depiction of the ensemble range captures the real evolution that happened in reality as well. So that is a way it is done. ESM should be easy to refine and upgrade as new process understanding becomes available that affect Earth system simulations. This is easier said than done, because model simulations, which take a long time, are often done with frozen versions of models, because you cannot keep changing it every day. Doing new simulations takes a long time, and testing the new additions also takes a long time, and validating them and calibrating them, etc. For example, a current modeling challenge is the ability to assess methods of geoengineering the climate. I'll show that as schematics in the next slides, maybe in the next podcast, but that refers to decision making based on Earth system models. Robust evidenced insights into the functioning of the Earth system will be essential if society decides that geoengineering is a course of action it wishes to consider, or in the event that it becomes a necessity if society is faced with potentially dangerous levels of climate change, but an inability to rapidly decarbonize its economy. So if it turns out that we are warming at a dangerous rate, for example, and we decide to go and throw some dust in the stratosphere, Earth system model should be able to say what are the consequences of that, what are the unintended consequences of that, let's say on ocean acidification, crop losses because of the reduced sunlight received because of reflecting and scattering it. For example, it would act like an analog to volcanic eruptions, right? So those sorts of ideas should be able to be, or ESM should have the capacity to deliver that kind of scenario, what if scenario information for geoengineering and other things we will look at. Model should be able to entrain observations from the Earth system to provide real-world constraints on the simulation. So we will look at what is called data assimilation to merge the models and observations. And the ESM should ensure the model state is consistent with the observed conditions. So there is some the validation of the model is needed. Such a model is then much more likely to increase our process understanding of the Earth system and more likely to make accurate predictions. Okay, that's how weather predictions are done. You assimilate, initialize the ocean and the atmosphere, mostly the ocean because that's the driver, and then you integrate forward, and that provides you reliability. Those are initial value problems, but climate is more of a boundary value problem because it depends on the ocean condition. Such a model is then much more okay. The improved accuracy is particularly important for shorter time scales, that is, decadal predictions rather than those with century or millennial time horizons. We will see where the uncertainties come from at the two different time scales. Decision horizons by human societies in general are considered decadal time scales, so now they are also being called societally relevant time scales. We will see that a bit more detail. Because these time scales, decadal predictions, in some respects are becoming increasingly important to policymakers planning adaptive and mitigation responses to climate change. So this is obviously one of the key purposes of developing Earth system prediction tools, because you want to navigate the future as safely as possible, as sustainably as possible, and these models better serve those purposes with some reliability, some known uncertainties, and some details at the scales at which decisions are being made, whether it's geoengineering or energy or reducing CO2 and so on. So it mixes global scale issues like CO2 and local and regional scale issues like dealing with disaster reductions, extreme events, vegetation loss, sea level rise, etc.